Hey there, and welcome to The Explainer. Have you ever looked at some random chemical in a test tube and thought, what on earth is that? Well, today we're putting on our detective hats. We're going to become chemical sleuths, and our mission is to figure out the secret identities of unknown chemicals. All we'll need are a couple of key reagents and our own sharp eyes. This, my friends, is qualitative analysis.
I mean, really think about it for a second. The water you drink, the soil our food grows in. How do we actually know what's in there? Is it pure? Is it safe? Well, that's where this comes in. Qualitative analysis is like having a superpower that lets you see the invisible, to spot the hidden chemicals that are literally all around us.
Take seafood, for example. We all love it, but sometimes things like heavy metals can get into the food chain from the water. In Singapore, the Food Agency, or SFA, runs tests all the time to keep our food safe. And they're using these exact techniques. It's qualitative analysis in the real world, not about figuring out how much of something is there, but just answering the simple, crucial question, what is there?
So here's our game plan. First, we'll go over the basic rules of our detective work. Next, we'll start hunting down our main suspects, the cations. After that, we'll track their partners in crime, the anions. We'll even learn to decode some gaseous clues, kind of like chemical fingerprints. And finally, we'll put it all together to crack the case. Ready? Let's go!
All right, Section 1, Chemical Detective Work. So, our mission, should we choose to accept it, is to take a complete unknown and figure out its identity. We're not using magnifying glasses, but we are looking for clues, really important clues, like a sudden color change, a solid that appears out of thin air, or a telltale gas that's released.
So, the official name for this is qualitative analysis. And the key word to remember here is quality. It's not about quantity. We're asking, hey, what is in this sample? Not how much of it is in there. Think of it this way. We want to know if there's lead in the water. Figuring out the exact parts per million, that's a whole different job called quantitative analysis. For us, it's just about the what. Okay, every investigation needs a prime suspect, right? In our chemical cases, those are usually the cations. Those are the positively charged ions. A simple way to think of them is as the metal part of a compound. And luckily for us, we've got two main tools in our kit that'll help us identify almost any of them.
These are our go-to tools, aqueous sodium hydroxide and aqueous ammonia. Now, whenever we add one of these to our mystery solution, we ask three simple questions. Number 1, does a solid suddenly appear? We call that a precipitate. Number 2, if it does, what color is it? And number 3, this is the real pro move, does that solid dissolve if we keep adding more of the reagent? We call that adding in excess. And trust me, it's a game changer for telling some of our suspects apart.
All right, pop quiz detective. You're in the lab, you've got a clear, unknown solution. You add a few drops of sodium hydroxide, and poof, a light blue solid appears out of nowhere. Based on just that one clue, who's your prime suspect?
If you said the copper-2 ion, you are absolutely right. That specific light blue solid is copper-2 hydroxide, and it is a dead giveaway. It's the chemical signature for the Cu2+ ion. Anytime you see that color, you should immediately be thinking copper.
Now here's a trickier one. When you test for the iron 2 ion, you get this kind of dirty green precipitate. But if you just wait a second and watch, you'll see it start to turn brown, especially at the surface. So what's happening? Well, the iron 2 is literally reacting with oxygen from the air and oxidizing into iron 3, which is reddish-brown. It's like getting two clues for the price of one. A classic detail to look out for.
Okay, now for the classic case of mistaken identity. You add sodium hydroxide to your unknown, and you get a white precipitate. Great. You add more, and it dissolves. The problem? Both aluminum and zinc ions do that. Their first clues are identical. So how do we tell them apart? We bring in our second tool, aqueous ammonia. Watch this. The aluminum precipitate won't dissolve in excess ammonia, but the zinc one will. Boom, that's our tiebreaker. Case cracked.
All right, we've got our cation suspect, but you know what they say? They rarely act alone. Every positive cation has a negative partner, an anion. Think of these as the accomplices.
And to track them down, we're going to need a whole different set of tests.
Now, I know this table looks like a lot, but let's just break it down. For carbonate, we add acid. Simple. Why? Because acid makes carbonates fizz and release carbon dioxide gas. For chloride and sulfate, the tests are kind of similar. We're trying to make a white precipitate again, but, and this is so important, do not forget this, you have to add dilute nitric acid first. This is to get rid of any sneaky carbonate ions that might be hanging around and give you a false positive. Once the coast is clear, then you add your silver nitrate for chloride or your barium nitrate for sulfate. That first acid step is absolutely crucial.
So, sometimes our chemical reactions leave behind one last piece of evidence, a gas. You got to think of these gases like fingerprints left at the scene of the crime. Each one has its own unique, 100% unmistakable test that gives it away.
For hydrogen, it's the famous burning splint test. You just put a lit splint into the test tube, and if hydrogen's there, you'll hear that classic squeaky pop sound. For oxygen, we use a glowing splint. So you light it, blow it out so it's just glowing red, and then stick that in the tube. If there's oxygen, it will relight. Pretty cool, right?
And let's not forget ammonia. Ammonia has a special power. It's the only common gas we test for that's alkaline, and because of that, it has a super simple test. All you need is a piece of damp red litmus paper. If you hold it in the gas, it'll turn blue. No other gas we look for will do that. It's a giveaway.
So there we have it. We've gathered clues for our cation, our anion, and maybe even a gas. But we're not quite done. A really great detective knows that the final step is to put all those pieces together, to look at all the evidence, and to build an airtight case for the identity of that original mystery compound.
And this right here, this is your secret weapon. This is the detective's master chart. It connects every suspect, every clue, and every tool we've just talked about. This is the perfect way to get all this information organized in your head, to revise for your exams, and just to see how it all fits together in one big picture.
And now it's over to you. You're the detective. On the screen is a flowchart puzzle, taken directly from the source material. This isn't just a hypothetical game. This is the exact kind of logical problem-solving you need to master to ace your exams. So, take a look at the clues. Follow the flowchart. Can you crack the case? Can you identify substances A through E? The investigation is now in your hands. Good luck.